Yesterday, we talked about ionic bonding, bonding between ions. And the thing about ionic bonding is that you have to, let's see, if we have H, no, let's not use H, never mind. Let's say we're sodium and fluorine. I'm sorry, what? Yes, it is. So here's the thing, folks. What we learned yesterday was that atoms like sodium have one outer electron, and they are perfectly happy to give up those electrons to fluorine, which has 7 outer electrons, and when it does so, it is able to be happy. Everybody's able to be happy because sodium then has its full octet of electrons in the 2s level underneath. Fluorine now has a filled 2s and 2p, 2s, 2p, 2s, 2p. Full octet, everybody's happy. It isn't giving the electron. Fluorine is taking the electron. One of the trends on the periodic table, which you're being tested on Friday, was called electronegativity. Who's willing to take a crack at telling me what that means? Yeah, it's okay.
It's like the strength they have to take the other electrons.
Right, right. It's the ability to take electrons. So the pull of the nucleus of one atom for the electrons of another atom, electronegativity. And what I didn't talk about really before was that the elements on the periodic table that form ionic compounds are very electronegative. Fluorine is the most electronegative. There's a scale of electronegativity, and it goes from the lowest one, well, the highest one is fluorine with a 4.0. And, you know, these are somewhere around, I don't know, 1 point something, I don't know what. And the way it works is that if two elements have a difference in electronegativity that's big enough, it's sort of like, you know, tug of war. You can have a stronger pull, but if you have elements that don't have a big enough difference in electronegativity, they can't take each other's electrons, and that's what I'm really going to talk about in a minute. Fluorine and sodium have a huge difference. Francium, or francium, as the English would say, francium. Actually, they would say like that. That would be, I don't know who would say that, but francium. Francium is a 0.9. It's the least electronegative, and so it gives up electrons incredibly easy to more electronegative elements. But let us look at a different example. Like, let's say hydrogen, which is also a group 1 element. It has 1 electron, and it would like to have either 2 electrons or no electrons, or that will suffice for getting a full outer shell. And let's say a different player, oxygen. Oxygen is, I'm going to draw a little line here so we don't get confused by all these atoms here. Oh, okay. So oxygen is S2, P4, which means it has this and this and this and this. And so how many does oxygen need? Right. What? 2. Right. And maybe you meant one more after this one. So yeah, one of the problems is that we actually need to have 2 hydrogens, right? But that's not the only problem. So alright, so here we have 2 hydrogens. So oxygen takes hydrogen's electrons and everybody's happy. We have a nice ionic compound, right? Wrong. No. Because the electronegativity of oxygen is still relatively high at something like 3.5 3.4, maybe it's 3.7, I don't know. What do I look like? A chart of electronegativities? No. But the thing is, that would work perfectly well if this were sodium, or if this were francium, or something else. But it's not. It's hydrogen, which has an electronegativity of about 2.4. And it's just not enough of a difference. I think you have to have a difference. Some people say 1.7, some people say 2. It has to be a big difference. What? Okay? The difference just isn't enough. And so oxygen can try, it can sort of try to pull that electron, but it just can't do it. And so think of it as a tug of war. If this element isn't electronegative enough, it just can't pull that electron away. And so, does anybody know what actually happens instead? They share them. That is correct. They will share them in what's called a covalent bond. So this is the other kind of bonding.
So the first one was Ionic Bond?
Right. The first one was Ionic Bond, and it turns out. I'll just draw this. Here's my quick little periodic table. Here's my quick little periodic table, and it turns out that ionic bonds happen mostly. Okay, well here's our noble gases. They don't do anything. Ionic bonds happen mostly between things in this column and things in these two columns, with a very few, with some that also come from the next column. So basically column 7, some from column 6, and always with these other things. So everybody else, for the most part, this isn't 100% true because the transition metals can also form ionic compounds. But let's not overthink this. Everybody else, like for example, okay, I made this too small, but group 5 and group 4. Okay, I really blew this. Here's another one over here. But like carbon is a big one for the covalent compounds. There's a number of them that are going to form not ionic compounds because they're not electronegative enough. But hello, go on and just don't kick the camera on your way in.
Move it.
Nicely done. Nicely done. Thank you. It was like the limbo. Okay. But anyway, so like these are the ones. Think of it like this. Some elements have enough power to pull away electrons. Some have to share, and that's really the point. So if you're not strong enough to pull them away, most people end up sharing. Covalent bonding. And I'll tell you, I'll really get into what the roots and prefix mean in this. So here's oxygen. I'm only going to draw the outer shell, the valence electrons, right? And here's oxygen with its 1, 2, 3, 4, 5, 6, right? S2, P4. It's 6 outer electrons, and it needs 2 more. And here comes hydrogen. And here's hydrogen's 1 electron. Of course, how many does hydrogen want to have? 2. And here's another hydrogen. And what happens instead, because neither one is strong enough to pull the electron away, certainly not hydrogen and not even oxygen, then they end up sharing. And the way that works is that, and this is the simplified version. Here's hydrogen. Here's its electron, which is I've drawn the electrons different colors, not because they're different. They're not. They're exactly the same, but just to show whose is whose. And so normally hydrogen's just there, and its electrons going around. It's actually going around in a sphere, but since I couldn't draw a sphere to save my life, we'll just do a little ring here. But once a covalent bond is formed, it starts to go sort of around the whole thing. And this is way oversimplified. It doesn't really go around the whole thing like this, but it sort of does.
That's why your markers die.
I know, I can do this. Sometimes I just do this by myself. I find this really soothing. It's kind of hypnotic, right? But so there goes, So in other words, the electron here effectively is also, don't forget, 1, 2, 3, 4, 5, 6. Here's oxygen 6, and so this electron effectively becomes an electron that oxygen has too, as does this one over here. And so everybody's happy because with these two, oxygen now has 8. So it's sharing, but it's good enough. So having it most of the time or half the time is good enough for this atom to feel satisfied with its lot in life. And then also the electrons from oxygen are also shared. And again, this is way oversimplified. This electron doesn't really get shared through the whole thing, but I'll tell you more specifically what it looks like in a minute. But the point is, this becomes part of now what we call a great big happy molecule. So finally, we've been in chemistry like, this is the 9th week. We finally get to use the word molecule. Up until then, it was only ionic compounds, which are known as formula units. This is a molecule, which is a group of covalently bonded atoms. Again, the octet is satisfied because everybody has 8. 1, 2, 3, 4, 5, 6. Whoa. 1, 2, 3, 4, 5, 6, 7, 8. Atoms. 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 Is that what's blocking?
There's only one hydrogen.
Oh my god. All right.